Hi, my name is Steve Ward, and I'm going to explain the fundamentals of Ethernet networks for use with PLCs, HMI SCADA, and edge devices. First, let's define what is a network. In industrial control and monitoring, a network is a set of devices sharing resources using data transmitted over digital interconnections. These devices can include PLC CPUs, I/O devices, but also network switches, operator interfaces, the edge devices themselves, other computers, and also drive systems such as variable frequency drives or servo drives. Devices use communication protocols over a digital interconnection to communicate with each other. And those digital interconnections are made up of telecommunication network technologies based on physically wired, but also optical and wireless radio frequency methods that may be arranged in a variety of different topologies. Today, Ethernet is the most commonly used network. So what is Ethernet? Ethernet was commercially introduced in 1980 and then standardized as IEEE 802.3 in 1983. Since its introduction, Ethernet has been refined to support higher and higher data bit rates, more nodes, and longer link distances. Originally, we used multi-drop coaxial cables, but these have been replaced by physical point-to-point links using multiple cables and repeaters or switches to extend the number of devices and the distance and the speed that's available. Ethernet was first adopted in PLCs starting in the 1990s and has replaced most proprietary field buses, although many of those proprietary field buses still exist and are still in use because the life of PLC systems can be quite long. With the Ethernet network, Ethernet stations communicate by sending each other data packets. Each data packet is a block of data that's individually sent and delivered. In the Ethernet network, each station has a globally unique 48-bit MAC address, where MAC stands for Media Access Control, and this relates to the physical layer of Ethernet where we send the messages, hence the Media Access Control part. Now, underlying Ethernet is the communications topology, and this is used to implement a protocol that's used at the industrial layer, such as PROFINET or TCP. So what is the Ethernet physical layer? The Ethernet physical layer is typically a cable, or today more often a set of cables, that sends data as bits, where each set of bits is put together into 8 bits to make a byte. In order to send data over the cable, each individual bit is represented as a voltage of plus or minus 2.5 volts sent over that twisted pair cable. And we use encoding to ensure that the voltage changes regularly. This aids us because we're using galvanic isolation via a transformer, and it makes sure that the data is regularly changing, and that gives us both the ability to have the data not revert back to zero due to cable inductance and capacitance, but it also gives us timing signals or clock signals which are embedded into the network signal. There's lots of types of encoding. Typically we're using Manchester encoding inside Ethernet, which means that depending on the status of the bits, as you can see in this diagram here, we do change the bits regularly, and the encoding system works out when the bits changed, but also keeps up the timing signals as well for synchronization. Now, original Ethernet used a single coaxial cable, but with modern cables we use multiple twisted pairs to allow multiple bits to be sent at the same time. Also, with multiple cables we can send and receive at the same time as well, and this is referred to as full duplex. And on the network, the byte may need more than 8 bits. Typically we have a start bit, a stop bit, and a parity bit, so each group of 8 bits to make up a byte has an overhead of 3 additional bits for the actual network itself. Now with Ethernet, we name the physical layers according to their specification. So typically we start off with 10, or that's the original standard. More likely today it would be 100 or 1000 or even 10G. This refers to the nominal usable speed or bandwidth over the physical layer in megabits. So 10 would mean 10 megabits, 100 would be in 100 gigabits, and so on. Then we have some words that refer to the signaling type. Baseband is most common, so you might hear about 100 base, which means it's a baseband signal where the network is modulated at the actual voltage and signal it needs to be. But we can also get broadband as well, or pass, and these refer to different signaling types where we modulate the signal over a different type of voltage or carrier. But these days baseband is most common. And then we have finishing off with some letters or letters and numbers, and this refers to the cable or medium we're going to use. So today a common network is 100 base T, so 100 refers to the nominal reusable speed, which is 100 megabits. Base is that it's baseband, and T means twisted pair. But we can also have some other types, twisted single pair, shortwave multi-mode fiber, for example, long-wave single-mode fiber. There's various forms of copper and so on. But the commonest is 100 base T, or 100 base TX, it's sometimes referred to as well. Now 100 base T, that's only 100 megabits. Many networks are growing in speed, and 100 or 1000 base T is becoming common. This uses these same RJ45 connectors, but then depending on the cable, we can achieve higher frequencies, and that allows us to have more data. A limitation of these 100 base T and 1000 base T networks is 100 meters though, and that's due to the cable type. Beyond 100 meters, there's just too much degradation of the signal, and the signal would no longer be propagated reliably. We can have fiber networks for longer distances, and these can also be used as the backbone of a copper network. So common ones are 100 base FX, 100 base SX, but we can also get 1000 base LX or 1000 base LX10, those are gigabit networks, and they're all used over a variety of different cable types with different connectors and supporting different distances depending on the transmitter type used and the actual properties of the physical fiber itself. To get the very long distances, you need to use very highly refined cables or fibers, which tend to cost a lot more. But you've also got the possibility to use repeaters to extend the distance as well. Now, Ethernet devices are connected together using a network topology. The simplest Ethernet network is a point-to-point connection between two devices. You can use a single copper patch cable. It's often called a patch cable, although modern devices can auto-detect if the signals are actually swapped over in the cable itself. But traditionally we would have used patch cables, or you could use a duplex fiber cable. So a duplex fiber cable, there would be one fiber for transmit and one fiber for receive. And with those two devices, they can be directly connected and you don't need any additional devices. But of course you're limited to those two devices on the network. Connecting more than two devices is possible in multiple ways, depending on how many devices you've got, what sort of distance you're going over, and there are then of course cost constraints depending on how fast you want to go. In legacy networks, we used to see a bus with multiple devices connected on the backplane, but that's very rarely used. Nowadays, we more commonly see a star or possibly a daisy chain type network. So with a star network, you have multiple devices connected to a single central device. Today, that would be a switch. With a daisy chain, each device has its own built-in switch, and you can connect from one device to the next, and so on, hence daisy chaining. And that can give you a longer network as well, exceeding the 100-meter distance, whereas a star would be limited to 200 meters with 100 meters of cable and the switch in the middle. Now, more complex networks would be arranged as a ring. If you use standard Ethernet and connect it in a ring, you will crash the network because all of the messages will be routed around the ring continuously, and very quickly, within a few milliseconds, the ring messages would have been repeated so often the network would be overloaded. But with using specific protocols, you can create a ring type network. Often this is used as the backbone between multiple devices. It can also be used in fault tolerant networks. And in this case, we have a central network with switches which are used to connect the devices. And those switches they have to be both supporting the ring topology as well as whatever ring protocol you're going to use. More and more networks today look like meshes, where you can get multiple devices connect to multiple other devices. And we also see tree type networks where it's a combination of topologies. So as long as you don't create a ring with devices that can't support it, generally most networks will work, and you can even connect different networks with routers and gateways, so we can have very widely extended networks. And that's what the internet is. It's a very large Ethernet network using specific protocols, TCP/IP in particular, that allows us to have all of these computers and servers all talking to each other across a very wide area. So this is what the traditional Ethernet bus topology would have looked like. Multiple devices connected on the backplane, used on legacy Ethernet networks. I don't think you would see this today. There's two versions, 10-base-2, which was limited to 185 meters using cheaper coaxial cable and simple BNC type connectors. And then there was the more expensive 10-base-5. So both of these are 10 megabits. 10-base-5 used a thicker coaxial cable with more expensive connectors. But the idea is you've got a single backplane there and devices were connected directly to that single backplane. In practice, it was quite complicated to use because you needed to use the connectors, you needed terminations at the end of the network, which were actually physical devices themselves. If a termination was wrong, or the connections were badly made, or possibly if a single device failed, or certainly if a single cable failed, then the network would fail. Also, if the termination was wrong or removed, again, network failure or reduced communication speed. So great technology in its day, but wouldn't really be seen today. So a star topology is much more representative of what you would see today. Now we have multiple devices connected to a single central device, which is today is a switch. There was an older device called a hub, but we don't see those anymore. With a hub, it was very similar to the previous technology, where you effectively had the backbone inside a single box and every device was connected to every other device. But today, the switch has more intelligence inside it, and it automatically routes messages between any two devices that want to talk to each other, allowing multiple other devices to also talk at the same time. Now, there is a single point of failure, which is the switch itself. But if the switch is of a normal grade, even simple consumer grade switches today, they're normally highly reliable. So unless you had some sort of power failure, it's very unlikely for the switch to go down. Cable problems are still an issue because of course cables are out there being exposed, and depending on the sorts of network cable you're using or the terminations of the connections, these networks, they're not perfect, but generally for today, they are very reliable because of the underlying quality of the electronics. Now with these networks, we can easily achieve 100 megabits, and even going up to a gigabit is very common. Today I'm seeing some devices coming out with native 2.5 gigabit communications, and it's also possible to get devices which support 10 gigabit communications, which is really a lot of bandwidth. The switch itself also needs to cope with all of that bandwidth, so depending on the quality of the switch, that may decide how much data you can actually put through. But generally, it's very easy to create these networks using copper cables, which is the T part, baseband communications, and 100 or gigabit Ethernet. Very straightforward and very common to see these. Some switches also have built-in fiber networks or router or gateway capabilities, so you can extend the network even further, and we'll see that in a minute. Here I'm showing 4 ports, by the way, but you can easily get 8, 16, 24 port switches. They're quite common, and you can even get stackable switches which allow you to combine multiple ports into a single switch. So let's talk a bit more about Ethernet switches. There's a variety of different switches available. The cheapest switches, which could be as low as $10 or €10 or £10, or I've seen them even cheaper. This is a simple unmanaged switch which has an electronic device in, and it allows the devices to communicate at a low layer by creating a one-to-one link between any two devices that need to talk to each other at any one time. As I said, prior to switches, we did have hubs which didn't have any intelligence, and all devices were connected to all other devices. So that meant if you had one device transmitting in a hub, none of the other devices could transmit, they could listen only. But with a modern switch, you can have multiple devices talking to each other. As long as any two are not talking to any other two at the same time, then you can have multiple parallel paths, which improves the throughput of the switch itself. Now, unmanaged switches, there is an electronic component inside which buffers the messages, and they can also coordinate devices with maybe different speeds. For example, maybe you want to connect a device that supports 100 megabits to a device that supports a gigabit. Switches can help with that. They can also help with either the full duplex or half duplex, depending on how many cables you've got in your wires. And they can also cope with the full or half duplex and the actual number of transmissions and so on, as well as some basic error detection as well. What many people use in industry though, and in office type networks and commercial systems, is networked managed switches, which have additional functionality. So with these managed switches, they have more computer power, and they can do things like tracking of network statistics using simple network management protocol, or SNMP. They can be configured with additional routing or blocking functions. So for example, you may want it so that some devices can talk to some devices but not others, and the switches can handle that. They could also handle network segregation using virtual private networks, which again is a more comprehensive way of having routing and blocking. And they can also perform a degree of redundancy by using protocols like STP or RSTP, which is Rapid Scanning Tree Protocol. That allows you to create a mesh with multiple connections, but the switch will handle which connections are active, and it will make sure that the packets aren't rerouted around the network. You can also get layer 3 switches, which can operate at an even higher level and can perform even more functions. And above that, of course, you can also get devices like firewalls, which can perform network protection. And then we have things like state detection and packet inspection. And there are a variety of different security systems that can be added at the switch layer or above as well, because cybersecurity can be very important in these networks. Now, switches do have a latency, but typically it's very, very fast, in the order of nanoseconds or milliseconds, and that's negligible compared to the overall device response time. Now, some Ethernet devices have built-in switches, allowing us to implement a daisy chain type topology. This is common with many PLCs using PROFINET, and also some devices which support Modbus and some other networks. The idea here is each device has a switch, and you have 2 physical ports, allowing you to plug in on one connector and then have another plug on another connector, and then you wire that to the next device and so on, hence daisy chain. Very common that there's no real physical limit to the number of switches. Although each switch does add some latency, it's not really enough to become an issue. But there is a problem here where you have an individual switch can become a bottleneck. If there is a lot of data going to the last device, all that data has got to be handled by the first device. So in very, very large networks, you wouldn't normally configure this, but this is normally intended for field level, IO level networks, where you still have high speed, but where there aren't going to be huge amounts of data. In a typical IO network, the data is sent frequently, maybe as often as once every millisecond, but there aren't huge amounts of data. Whereas if you try to run video over this, then again, you could find that individual switch can become a bottleneck. You've also got the potential issue here that if the first device fails, or if any of these cables fails, any device further down would fail, and that's where this MRP protocol comes in. MRP is Media Redundancy Protocol that allows you to create a fault-tolerant network by wiring the last device back to the first device, so you need an extra piece of cable. But what the MRP system does, there's a Media Redundancy Manager and a Media Redundancy Client, and they handle the communications a bit like in the RSTP system to make sure that the packets aren't endlessly repeated around the network. Another sort of network you might see is the ring topology. In this one, we have a central network with switches, and then those switches also have additional connections to connect your devices. So the backbone or ring, that may be based on fiber, and it can also be a fiber network or a copper network, but often it's fiber. And then you have the additional ports to connect your actual devices. And this same sort of ring terminology is also used for that MRP system as well, as I just explained. So this allows us to extend the number of devices, but it can also give us more reliability as well by having fault tolerance. Here is a mesh type network. With this, we have multiple devices connected to multiple other devices, and we don't really care what device connects to what other. The RSTP or other mesh protocols, they work out which devices have the best throughput, and they coordinate the network accordingly. But if one of those networks or one of those devices were to fail, the RSTP or the mesh protocol can reroute messages around that failed device. As long as you haven't got a single point of failure, like the device over on the right hand side there that's got 4 devices connected to it, that's a single point of failure which will prevent communication between the left and the right. But for the other devices, any single point of failure or any cable failure, the system would be able to route around that and to continue working. So it gives you 2 benefits, gives you some redundancy, but also it means you don't need to worry about your cable layout. So you can just plug any device into any other device and know that it will still work. However, I should emphasize, this is normally done at the switch level. You wouldn't normally connect the actual devices together like this. So normally these devices would be switches, and then the actual devices would be connected to the mesh backbone via an individual single cable. And this is what we see in practice, a combination of topologies. There may be a backbone with some devices connected. There may be a small local network with a switch with several devices. The switch might be used to extend the network by connecting to other devices. We may even get devices with the sort of dual switches built in, and they can be used as switches themselves. And again, depending on what protocol you're using, it's normally pretty straightforward to connect this. The only issue here really is we've got this extra cable over on the right hand side in red. If you were to add that cable into a network with devices which don't support it, you've now created a ring which will crash the network. But commonly, as long as you're taking care of, that you're not creating a ring, these are very common to see in typical installations. Now in the previous slide, at the physical layer, all those devices are connected, but that can cause problems with addressing on the network. So what some users like to do is have separate Ethernet networks, each with their own addressing structures, and then they are connected together using a router or a gateway. So here we've got 2 backbone networks, each with their own sets of devices. And then in the middle at the top, we've got a router which acts to connect those messages, those devices, and it only sends messages which are intended for the other network. So this can do 2 things. It can be used for helping out with the actual addressing on the network, but it can also be used for isolating the networks to improve performance. And that router could also be connections between 2 different offices or 2 different buildings or 2 different sites. So this allows us to implement like a wide area network system as well. So the router can also perform security functions for cyber security. But this is a great way of extending networks. And that router system, that can include fiber as well to extend the distances. So there's a lot of the capabilities here of how separate networks can be connected together using these sorts of devices. So this is similar to the previous slide, but now we've got a cloud or WAN connection, WAN being wide area network as opposed to local area network or LAN. So in this case now, these 2 networks could be very far apart, and that cloud, that could be the internet, or it could be a private connection between 2 different offices of the same company. And normally if we get up to that sort of cloud layer, normally that's either a fiber or an RJ45 copper type connection, and the actual details of what's in the cloud or the WAN, that's normally out of the scope of someone that's performing PLC type projects. All you know is that you plug into that network and your messages will be routed to the far end, and the cloud or WAN connection takes care of that. So far we've talked about the physical layer of Ethernet, which is the cable and the way that the bits are sent across the message, and it actually extends slightly beyond that. But now it's a good idea to introduce the Open Systems Interconnection model, and this provides a basis for coordinating standards development for the purpose of systems interconnection. The idea is if multiple vendors wanted to create a protocol running across a certain network, the OSI 7-layer reference model would give them a basis for what that network might look like and how they can coordinate their efforts to make that network work. So with the OSI reference model, the computers are communicating, and they are split into 7 abstraction layers to actually define how the communications work. So we're going to start at the bottom. If you look at layer 1, this is the physical layer responsible for sending bits between devices. So in Ethernet, this is like the underlying electronics. So it's the transistor which sends a bit, the transformer which isolates the network, because Ethernet is normally isolated via small transformers. It might also include the LED or diode that's used if you're sending light across a fiber cable, but very much responsible for sending a single bit. And above that you have layer 2, which is the data link layer, which Ethernet also encompasses, and this provides node-to-node data transfer, including low-level error detection and correction. So now we're talking about the modulation, we're talking about bytes rather than bits, we may be talking about frames or packets, but very low level of data. We don't define what the data is, but we are defining now that some data is being sent. Now, when we get to layer 3, we're no longer talking about Ethernet now. We're now talking about some sort of protocol that sits on top of Ethernet or whatever your network is. So layer 3 is the network layer that provides a means of transferring packets from one node to another, including longer messages than a single packet and selection of a route through the network. So with Ethernet, a single frame or network message is only about 1,500 bytes long maximum. If you wanted to send a video file or a file that was larger than that, 1,500 bytes, that's where layer 3 comes in, and the protocol helps sort that out. Also, if you're looking at these mesh type networks, again, that's where layer 3 comes in to work out how to select that route through the network. Layer 4 is the transport layer, and this provides a means of transferring variable length data sequences from a source to a destination host, and from one application to another across a network, including provision for quality of service. So it's adding on to what you get with layer 3 to, again, better define what that data is and how it's handled. Layer 5 is the session layer, which involves setting up a session. So again, like your telephone call, you pick up your receiver or use your mobile phone, you dial the number, the other person answers, you have a short conversation to establish who you are and why you're phoning, and they agree, and then you have your message, and then at the end of that you'd say bye and hang up, or put your mobile phone down, or however you turn it off. So this session layer is doing that similar sort of function. It's creating the setup, controlling the connection, ending teardown between two or more computers. We still haven't really defined what the message is. There's lots of reasons why you might telephone someone. So this is where the presentation layer comes in. It establishes data formatting and data translation. So to make sure that what you're sending is in a format that is understood by the other device. And then finally, we have layer 7, which is the application, which is the user level protocol, such as if you're downloading web pages over the internet, you're typically using HTTP or HTTPS, which is a specific protocol defined how to handle web pages. There's actually a layer on top of that, which is layer 8, which is the actual application itself. And that could be further subdivided too. So for example, if you're reading web pages, layer 8 could be referred to as the combination of the server serving up the web pages and the web browser that's actually interpreting those web pages and displaying them. And potentially there's a layer 9, or maybe that's combined into layer 8, which is what are those web pages? For example, are you using a CRM? Are you using YouTube? Depending on what that is, they could be additional layers. But we're getting beyond what the OSI reference model is establishing now. And with these 7 layers, this allows 2 people or more developing a standard for systems interconnection to define what they want to do. Now in practice, we don't implement every layer, and sometimes we combine layers. So for example, with Ethernet combines layer 1 and layer 2 into a single physical protocol that you can use to send data. And you'll see other applications of how we can use the OSI 7 layer and compare, and maybe not every layer is used, or maybe some layers are combined. You'll see that in later slides. So if we're talking about protocols, what is the most common protocol in use today? It's probably TCP/IP. TCP/IP specifies how data is exchanged over wider networks and smaller networks, and also over the internet. It provides all of those layers you've seen previously, from layer 3 up to layer 7, or layer 6 even, to define the end-to-end communications that identify how the data should be broken up into packets, how it's addressed, how it's transmitted, how it's routed, how it's received at the destination, and also covers recovery and timeouts and errors and so on. So TCP/IP is really 2 protocols. you've got TCP at the bottom, which defines how applications can create channels of communications across a network. So again, it's like your phone call. This is the initial negotiation you have when you phone someone up and you start talking to establish, who are you, what are you going to talk about, what language are you going to use. Presumably you're both talking English or at least some common language. So the TCP sort of protocol is establishing all of this, how the message is assembled into smaller packets, how they're transmitted, how they're reassembled. Again, if you think of the limitation of Ethernet, you can only send 1500 bytes at a time. But if you've got a very large message, you might split it up into 1500 byte chunks, but depending on how the message is sent, some of those 1500 bytes might arrive in a different order to how they were sent. So TCP manages how those different packets are reassembled so that you get the right file in the right order and it's not just chopped up into something that's meaningless. Now TCP is stateful in that it transmits a single message, and then based on that message and the initial communications, the connection remains in place until all packets have been received and reassembled, and then the transport layer can close that state of communications. Now the IP layer, this is the one where maybe you're a bit more familiar if you've ever configured an IP address. This defines how to address and reach each packet to make sure it reaches the right destination. So this is more about network addressing. So what the IP protocol does is it looks on the local network to see what the IP address is and if the device is on the local network. And then also in gateways, the IP address is used to determine if the message needs to be forwarded to another network. And together, TCP and IP, they define how those messages are sent across local networks and the internet. So here's how a TCP connection is established. You have your client, which is the device that is requesting services, and then you have your server, which is the device that's responding. So again, in a telephone call, if you're initiating the call, you're the client, the person at the other end is the server. So we start off with a SYN message. This requests a connection from the initiating device to the other device. And when the other device receives that SYN message, it sends a SYNAC, which acknowledges the SYN request. And then we have the third part of the three-way handshake, which is to send and acknowledge, and that acknowledges the SYNAC. And the reason we have this three-way message, if there was just a SYN with an ACK, then potentially the first device might not have corresponded correctly, or it might not have sent all the data it needed. So we've got this three-way transfer to make sure that all of the correct data is established, and that's defined by the TCP standard. Now once the ACK is received by the server, that means that both devices are now communicating with each other with a connection. And now what can happen is you can have the data transfer, and then there's a FIN which terminates the connection when either data transfer has been sent, or if one device decides, the server decides it doesn't want to send any more data. So there will be a timeout if there's no communications. The default is 60 to 90 seconds. The client sends the SYN message, and then it waits that default time for the server to respond. If it doesn't respond, then it might try and send another connection request, or it might just give up and you get an error message at the application layer. And the reason for this is you want to make sure there's a length of time before you try and send too many messages, otherwise this can overload resources. On the other hand, that default timeout might be too long, so in some systems it can be reduced, because maybe if you're on the local network you would expect a faster response. Waiting 60 to 90 seconds might be too long. But the default, depending on the system, is between 60 and 90 seconds. If there's no response, then the client gives up. Or maybe if you're halfway through data transfer, maybe one of the devices is turned off or decides not to respond or can't process the data, or perhaps there's a network failure. So in that case, the devices will also wait that time before they then close that connection. So TCP uses a connection, and there is some protocol overhead, sending that SYN, the SYNAC, acknowledging the SYN, and then sending the FIN message. For a very small message, particularly in industrial automation applications where you might only be sending a few bits or bytes, that's potentially a lot of overhead. So there is an alternative to send using UDP protocol. So this is again used to send messages within an IP network. So we've got the same IP protocol as before, but now we've got UDP, which stands for User Datagram Protocol. And what UDP does is it doesn't require a prior communication. It's effectively a simple connectionless communication model with a minimal protocol mechanism. Very good for where error checking and correction aren't necessary, or maybe they're performed at a higher level. And effectively what you do with UDP messages, you just either send it to a single device, and you just send it, that's it. There's no timeout, there's no waiting, there's no acknowledgement. You just send the message. You can send to a single device, you can multicast to multiple devices on the network, or you can broadcast to every device on the network. It's very good for industrial communications, but it's also useful for things like maybe voice over IP, where if a packet is lost, then it's not going to be too much corruption to the overall message. It's also used for streaming media, for some video applications. And very good where maybe you just want to send data and you don't care if the other device actually receives it or not. So much lower protocol overhead, but it does have the disadvantage, you don't know if the message is ever received. All you know is if you're the client, you sent the message, the server, you don't know. Having said that, some protocols can embed messages within the UDP IP data, and you can create a handshake that way, but UDP is really intended for shorter, smaller messages where you don't necessarily need a response. So there's another aspect of TCP/IP and UDP/IP applications, which is they use datagram sockets to establish host-to-host communications. These are also known as Ethernet ports, and we're distinguishing port at the software layer here rather than the physical port where you plug in your cable. So the way the port is used, an application binds a socket to its endpoint of data transmission using a combination of both the IP address but also a port number. So the idea of having the port number, it just helps multiple devices communicate, and it also gives you a bit more context around what the data would be expected to be, because we have common port numbers for common protocols. So the port number itself is identified by a 16-bit integer value. This allows port numbers between 0 and 65,535, although sometimes some of these port numbers are reserved. So for example, a common port that we use is port 80. 80 is used for HTTP over the internet, and what you might see then is a socket datagram would look like the IP address with a colon and then the port number. So 192.168.0.101 #80. Now if you didn't include that 80 in a web server or web client, the web browser, then the web browser assumes port 80. But you may have reconfigured your web server to be running on a different port, and there are alternative ports like 8080, in which case you change that number at the end, and that way the connection would be made to that alternative port number. And if you didn't specify the port number and you just used the default of 80, if that port wasn't there, then you wouldn't get a response. So that port is just an additional way of specifying communications between the client and the server device. It also helps from cybersecurity point of view, because as well as blocking IP addresses and blocking specific devices, you can block ports. So if you had a firewall and you only wanted to allow communication to the internet using the standard port, you could block all ports except for port 80, and that way only Ethernet data to the internet would be allowed using that port 80. Now that doesn't make you completely secure, because people could still inject other messages through port 80, but it does reduce the attack surface for a lot of other attacks that people might be trying by limiting that number of ports that are in use. So that's another reason for ports. It helps understand what the data might be, but it also allows you to implement higher levels of cybersecurity, as well as being used at the lower level for the interconnection of the system. You won't always see port numbers. Often the port number is assumed, and with many industrial protocols, they default to a port that can't be changed. So for example, with Modbus, that defaults to port 502 and you can't change it. So again, from a firewall point of view, if you blocked port 502, that would block any Modbus TCP communications over that network. So how does TCP/IP compare to the OSI 7-layer model? Well, if you look at this diagram, you'll see we've got the OSI reference model on the left and then we've got the corresponding TCP/IP conceptual layers over on the right. The physical and data link layers, which are later layers 1 and 2, they correspond to the actual Ethernet network itself. IP corresponds to the network layer, and then the TCP or UDP, that corresponds to the transport layer. There isn't really anything at the session, presentation or application layers. That's defined by the application protocol you use. So for example, with HTTP, that would implement any sort of session control and the presentation and the application layer. Interestingly, with HTTP, there isn't actually any session control. Although you have a TCP connection between the server and the client, the actual HTTP session itself is connectionless. So each time you send a HTTP request from your web browser to the server, all of the session handling, so for example, if you've logged into a web page and it needs to keep track of you, or maybe you're on a shopping page and you've put items in the basket, all of that needs to be actually handled at the application layer. It's not really handled by any part of the protocol. Now with Ethernet, we have got the concept of sending frames and packets, which are the physical bits or bytes which sent over the network. So with Ethernet and TCP/IP, we have a sort of nested set of packets or frames which are sent over the data. So we have the overall frame at the high level. If you look at this top line here, you'll see that's called the overall frame, and part of this is mandated by the Ethernet system itself. So first of all, we have a 12-byte interframe gap between messages. So that's used to give the electronics time to actually process the previous message and settle down and wait for the next message. We then have 7 bytes of preamble or synchronization, which is where the sending device is now sending a certain set of bits and expecting the other device now to see those bits and synchronize the clock, and then start to expect to receive a message. So interestingly with Ethernet, before we even send any data, we've sent here 19 bytes of data which doesn't actually do anything but is just used for synchronization. And then there's an additional byte which doesn't do anything, which is the start frame. So this is actually 1 byte that says the next thing you will receive will be the actual message itself. So we have the overall frame, and that's at layer 1. And then at layer 2, we have the layer 2 frame, which is now where we have some actual human readable data that would mean something to us. So we start with a low-level address called the MAC address, or the Media Access Control Layer address. So this is normally expressed as a big long hexadecimal number, but it actually consists of 6 bytes. So we have the destination address we're sending to, and then so the system can identify the messages, we have a source MAC address as well, which also consists of 6 bytes. So the system overall knows who we're sending from and who we're sending to. Now it is possible for a human to read the MAC address, but it doesn't necessarily translate into anything that's easily understandable. It is 6 low-level bytes, again normally expressed as a hexadecimal number that we can read. What also happens is the MAC address is normally split into 2 parts. There's like a vendor part, which is the first 3 bytes, and then there's the 3 bytes to indicate the individual device that vendor has actually produced. And those MAC addresses are normally hard-coded into the device, but not always. In some devices, we vary the MAC address from message to message to obscure where the actual message is coming from. But generally it's a fixed MAC address, at least for the period of the communications, and it's used by the low level of the system to actually decide where to send the message. Now the next part of the layer 2 frame is the virtual LAN network part, which is standardized under the 802.1q standard. This is 4 bytes, not always used, but this can be used to define things like quality of service, as well as some other information defining what sort of network it is. VLANs are often used to segment networks. The idea is you can send, say, several different messages over the same network, but using a different VLAN, they are completely isolated from each other, and devices can't read messages which are intended for or sent from another VLAN. So it's an additional security part, but it can be overcome at the software layer. But it is often seen in these large structured networks where we segregate networks into multiple VLANs. There's then a message type, which consists of 2 bytes. And then we get the actual message payload itself. So the message payload is between 46 and 1500 bytes. And that's padded with zeros if it's less than 46 bytes. So you can't send less than 46 bytes. That's the minimum. And then finally, there would be a cyclic redundancy check of 4 bytes. The cyclic redundancy check is used by the receiving system to calculate if the message has been corrupted at all. And if it has been corrupted, then it can be ignored, and then the sending device would have to resend that message. Now, within the payload is where we would have our higher level protocol. So in the TCP/IP network, inside the payload, we have the IP packet itself. So the IP packet also has its own protocol specification. So there's a header, there's the length of data, there's some metadata, there's some description about the protocol that's being used, there's a checksum, which is additional checking information, and then there's the IP address now. So the IP address is normally a 4-byte number, and it's a bit more easy for humans to read. And again, you get the source IP address and the destination IP address, so the system knows how to route those IP packets around the network. And then you get the actual data itself. So because we've got some additional data here, we've actually lost some of our data that's available in the overall payload, and we've increased the amount of overhead in the system. So there's more and more data being added now, which the system needs to be able to process it, but that reduces the amount of data we're actually sending over the network, even though it's essential, but it does affect how efficient our communications is. Now, on top of the IP packet then, we further subdivide that data into the TCP packet. So now we have the source port and the destination port. I mentioned these. We have a sequence and acknowledge bits, some more metadata, another checksum, and now we have the final data itself, which can be interpreted at the application layer. So each of these protocols is effectively embedded inside the other, and then embedded inside the overall frame, which is what is actually sent on the network. Now, the good news for most people is you won't get involved at this level. It is possible to use diagnostic tools like Wireshark, which can go down onto the network and bring back the individual bits and bytes. Wireshark is really good because it understands a lot of common protocols, even above the TCP/IP layer, but it also understands about what's in the TCP and IP packets, and also even what's sent at the layer 2 frame. So Wireshark is something that people use for very low level network analysis. And also, there may be tools like deep packet inspection and firewalls and so on, which also use these data to control how messages are sent. But generally, for most of us, we don't need to get down to this layer. The fact of the CRCs and the checksums, as well as additional data checking at the higher protocol levels, they normally help us understand if the message is received and why not. And normally, it's rare for a message to be corrupted, but if it is, the system will resend it automatically. I think I did some work a long time ago, and it's only one in tens of millions of bits which get corrupted, and in that case, if the message can't be recovered, it's just resent, and most systems wouldn't even notice that. The message would just be resent. You might see that at the Wireshark level, but the system itself, it might increment a diagnostic counter to tell you about failed messages. But in a system that's operating correctly, there would be very few of those missed messages, and the counters would all be very low. So it helps to understand the low level of what's going on. But again, as I said, in many systems, it's transparent to you as a user, and it's only when you get into detailed network diagnostics do you really need to understand what's happening at these layers. So although the number of errors that is likely to occur is very low, how do we actually detect the errors? Well, as you can see, it's performed at multiple levels. You can use individual bytes or collections of bytes for a parity bit. Parity bits at the very low level can be used for single error bit detection. At the message level, you've seen there with TCP/IP, we use checksums and CRCs. And the typical way these are calculated is we take a number or a byte and those numbers are from 0 to 255. And what we typically do is, at the sending end, we add up all the bytes in a packet. Say the sum is 157,231 of the sum of all the bytes. What we might do is take the last two digits, 31, as the checksum of the packet, and we'll add those at the end of our packet. What the receiver does is it adds up all the bytes again, and it checks for its calculation of the checksum is the same as the one that's in the message. If they don't match, then that indicates data corruption, and the receiver can ask the sender to resend their packets. Now, it is possible that two or more errors could cancel each other out, and this is why we have checksums at multiple levels. It's very unlikely that two errors could result in two different checksums which are calculated differently from both ending up the same. So it's extremely unlikely that two or more errors that could cancel each other out would not be detected, because we've got these checksums at multiple levels. Again, the error detection is normally handled at the protocol level. It's not normally something the user needs to worry about, but on some variable networks, again, you can look at those error counters, or you could use Wireshark, and that might determine if you've maybe got a dodgy segment on your network. Maybe there's something that's at the limit of its distance, maybe you're getting a lot of electrical noise, and if you do get very high levels of resending or high levels of errors being detected, that could indicate a problem with that part of the network or with a particular device. So this is useful, but normally in modern applications, you get a human readable message telling you what's going on, rather than have to go down to a really low level to diagnose this. So let's talk a bit about PROFINET or PROFINET. PROFINET is a standard interconnection protocol for connecting controllers to I/O devices. And typically that controller would be a PLC or possibly a DCS or some sort of controlling device. And if you need full details, you can head over to https://profinetuniversity.com and you can read all about PROFINET. But here's a brief overview. PROFINET is a real-time protocol, and it's implemented in two different formats. There's PROFINET RT, which is real-time, and this provides for I/O cycle times down to 1 millisecond using standard Ethernet. So with standard Ethernet, you can have I/O devices such as inputs and outputs using discrete or analog inputs connected to your PLC, and you can configure the cycle time at 1 or 2 or 4 or 8 or 16 or so on milliseconds, and it will give you very good response using the PROFINET protocol running over the top of Ethernet. If you want faster communication times, we can do that with PROFINET IRT, where IRT stands for isochronous real time. And this gives you I/O cycle times down to 31.25 microseconds with only 1 microsecond of jitter. But in order to be able to achieve that, your sending or your master device must have a special Ethernet interface. The I/O can be the same for both RT and IRT, but the sending device, the controlling master device, does need special Ethernet hardware to be able to achieve these cycle times. Now, PROFINET is ideal for industrial networks. It runs directly over Ethernet, which gives it very high performance, but it also uses TCP/IP for configuration and diagnostics. One characteristic of Ethernet is Ethernet can support multiple protocols at the same time. We've got the Ethernet frames that we saw earlier. Although the payload is often TCP/IP, that payload can be a different protocol. So the payload could be PROFINET. And then by sending multiple packets, one after the other, then you can send those multiple protocols simultaneously over that same piece of copper or fiber. So PROFINET is a standard that runs over Ethernet. It also uses TCP/IP. However, the PROFINET network part itself, the protocol, it will support standard Ethernet networks. It supports unmanaged switches, but it's not routable, and it can't pass between networks connected by a bridge or router. So this does again help you if you wanted to have a network between your PLC and I/O, but also connect it to another network but not overload the other network with messages. Then because PROFINET is not routable, you could just put a router between them and easily segregate the networks that way. Now, PROFINET is easy to use. There's a discovery and configuration protocol that allows devices to announce themselves on the network. And then using a DCP tool, you can detect those devices and then configure aspects like their name, their IP address, and maybe anything else that's required. At the application layer, there's also a GSDML file which is used in the application, and the DCP tool is used to configure the low-level configuration. The GSDML file is more for the high-level configuration, like what the I/O device does and possibly how the addressing works. Now, PROFINET is connection based, and what happens is during normal operation an application relationship is established so that the controller can write outputs to and read inputs from an I/O device. The application relationship is a bit like the TCP IP connection. It's like a SYN/ACK ACK response, and then it defines what the connection will be, including configuration and so on, and then it operates on a cyclical basis. So it defines the period of the data down to 1 millisecond using RT or 31.25 milliseconds for IRT. We talked about MRP when we were looking at the network topologies. Media redundancy protocol allows a ring to be created and supports any single point of failure with recovery within a few milliseconds. We have a media redundancy manager which monitors the ring topology, and it determines how to send the data so that no messages are lost, but also so that no messages are duplicated. However, MRP does need MRP aware devices, and if you're using switches on the network, you can use unmanaged switches, but then the unmanaged switch won't be detected if it fails. So normally it's preferred to use PROFINET level devices, which are both MRP aware and can handle that MRP switching themselves, as well as being handled by the media redundancy manager. PROFINET also supports redundancy with two application relationships so that an I/O device can work with two controllers in redundant systems. This does, again, the redundancy capable devices, and if you're using switches, they also need to be able to support the S2 system redundancy. But the idea is we can build up a high fault tolerant system with a combination of redundant or hot standby PLCs, and then we can have a fault tolerant network, and then you can also have redundant I/O if you want it. So ideal for critical and high performance applications. So how does PROFINET compare to the OSI 7 layer model? Well, again, you've normally got Ethernet at the bottom, and it will run over Wi-Fi, but normally you'd be using a copper cable, possibly a fiber cable. So you can see you've got Ethernet at the bottom layer with the physical and the data link. And then for the configuration and diagnostics, you've got TCP/IP and UDP and IP. So IP is used at the network layer. With TCP for configuration and diagnostics, UDP can be used for fault messages and asynchronous messaging. But on the PROFINET side, it's on the right, you've actually got the PROFINET protocol, which uses those low-level Ethernet frames, and it doesn't use TCP or IP at all. It's its own protocol running directly on the Ethernet network. And then above that, we have the PROFINET real-time data. So that's where you have the RT or the IRT part. And typically, RT is used for standard I/O, discrete in, discrete out, analog in, analog out, where you have a high-speed cycle. But the IRT is used for devices which need even higher cycle times. So typically that would be for servo motion devices. But you can see how both networks, both operating on Ethernet, and how they correspond here to the OSI 7-layer reference model. So if you're configuring PROFINET, what does the topology look like? Well, it's very similar to what we've seen. A standard star topology using a switch would have our controller connected to one port on the switch, and then our I/O devices connected to additional devices on the switch. There is a single point of failure, which is the switch itself, but otherwise, of course, if everything is running normally and those switches are very reliable, then you're not really going to have any issues with this. In this system, of course, you've also got a single point of failure in the controller itself. PROFINET networks can be extended. In theory, PROFINET supports up to 255 devices connected to a single controller, and possibly even more in a larger system. So it is possible to extend the number of devices by adding additional switches and linking them together. The only thing to note is that PROFINET is not routable, so it has to be a single network with no routers or gateways. But using the correct combination of switches, you can extend the distances to pretty much as far as you want, and you can have pretty much as many I/O devices as you like, up to the limits of what the controller will support. Latency would be an issue. Again, if you think about that early switch on the left, that's handling more data than the switch on the right. So potentially there could be issues there, but normally those switches are operating down at the microsecond level, where your network of PROFINET is operating at the millisecond level. So we're orders of magnitude different. The only time this would be an issue is if you were using PROFINET IRT and you really needed that very high speed 31.25 microsecond transfer. So generally, systems like this, very easy to create, and with standard PROFINET with simplex systems without MRP, that can be any switch. It can be a standard switch, managed or unmanaged, layer 2 or 3. It's just a switch. The network doesn't really care. Now, the problem with the previous topology is you end up having to buy lots and lots of switches, and industrial switches don't tend to be cheap. So this is what we find in many common PROFINET implementations today. Multiple devices are connected to each other using a daisy chain topology where each device has a built-in switch. Now, the benefit of this is you don't need any additional hardware. All you need is your Ethernet cables between the controller and between each I/O device. Again, this allows you to extend your distance, and it's normally not an issue in terms of reliability. But you have got single points of failure. Each of these cables and each of these I/O devices is potentially a single point of failure, but so is the controller itself. So for most applications, this would be fine, and this would give you very good levels of availability. Of course, the key benefit, because the switches are built into the devices, you don't need to buy any additional hardware. So what if you're worried about one of those cables being broken? This is probably the thing that goes wrong most on sites. Cables break. They might be under heavy stress loads. Someone might damage the trunking they're in. Forklift trucks drive into them. That you get physical damage. So those cables are probably the least reliable part in a distributed system. So we can use this ring technology using media redundancy protocol. Media redundancy protocol has to be supported by every device, but the idea is we've got a switch built into each device. Why not wire the last device back to your first device? And if we did this with normal Ethernet, this would create a ring which would crash the network. The packets would move around the ring, they would be continually repeated, and the amount of data would overload the network very quickly, in the order of a few milliseconds. But with MRP, there's like a software switch, and what happens is the controlling device, the media redundancy manager, it doesn't route the messages around as long as the network is working correctly. But if any device fails and the network message isn't detected as being received after it's being sent, or if any one of these devices sends a message saying that it has failed or is not communicating, or that it detects a problem, then what the controlling device can do is it can switch the direction of the messages to the other way around the ring. So every device continues to receive a message, even if there's a cable break or if a single I/O device fails. Now, what happens if there are multiple failures? Well, that depends. If the two devices in the middle both fail, then you haven't lost anything, because the controller would communicate with the left device using the left port and the right device with the right port. But potentially, if the two devices at the end failed, your devices in the middle would no longer be communicating, because they would no longer be receiving data. So there are failure modes where you can lose the entire system, but that would need a subsequent failure. So as long as there's only needing to survive a single point failure, MRP is a really good methodology for using that. And it's very difficult to handle multiple failures anyway. Normally, if you're up to the area of a second failure, maybe you've got a redundant PLC, one PLC fails, the other PLC fails, your system has failed. Maybe there's some more catastrophic failure, which is also very common, We see issues where maybe a device catches fire, or there's a fire in a panel, or a flood. So, devices in those cases can be catastrophic, and that's very difficult to calculate. But you can do failure mode effect analysis to try and understand effectively what might go on, and use that to guide how the system will work. But normally, if you've got some sort of disaster like that, the fact your machine is stopped is often the least of your worries. So here's an extension of the MRP protocol with an additional controller. So we've now got two PLCs, a master controller and a backup. Typically these operate in hot standby mode, so the master's in charge. And then if there's any failure with the master, or if it's taken offline for maintenance, the backup controller would take over. So this gives us an extra level of availability at the controller level. And now we've got high availability at the PROFINET level. And we can also duplicate the I/O if we want to as well. I do see some devices which have additional network capabilities with more cables, but I normally run the availability numbers and they normally don't help you. There are very few failure modes where that can help, but generally, if you've got that high level of failures where multiple things are going wrong, you're probably at a more dangerous situation than just a PLC failure now. But this system, this is very good. It's called S2 system redundancy, and it will survive any single point failure, including control failure. And it also allows online changes to configuration and firmware updates. But the issue is all of the devices in the system must support both MRP and the S2 system redundancy. So let's go back a bit and talk about Ethernet and the underlying MAC addressing. So MAC address is a low-level address used at the physical network layer. And the actual MAC address is normally expressed as 12 digits. If you remember, it's a 6-byte value, and we represent it using 12 digits of 4 bits each, using hexadecimal notation of 0 to F. So the way this works is each device has a MAC address assigned by the vendor during the manufacture. For example, if you look at Emerson PLCs, they often start with 08 and then a colon 00 colon 19. That's the top part of the MAC address. They are owned by Emerson, and then the bottom part of the MAC address is assigned uniquely to each device. And if you're looking at an unmanaged switch or a layer 2 type switch, that uses the MAC address to know which port to send a message to. There are some devices which do change MAC addresses on different networks to prevent tracking. But the device itself would normally detect which network it's on, and it would use that same MAC address on that same network to make network management easier. You wouldn't just randomly change the MAC address because the network itself would take some time to recover. And what we have associated with the MAC address, we have a protocol called ARP, or Address Resolution Protocol, and this is used to map MAC addresses to IP addresses. So when you're working at layer 3 and above using IP, each device has its ARP table that's used to convert that IP address into the low-level MAC address. Now I have hints in here, sometimes MAC addresses change. You might replace a device, say for example, if you've got a laptop on the network, you might have a failure of that network, that laptop, you get another laptop from your IT team, it has the same computer name, same IP address and everything, but it will have a different MAC address. So sometimes the ARP table can get confused. It should recover by itself, and it should detect the new device with the new MAC address, even though the IP address and name are the same, it should recover. But if not, sometimes you might want to clear the ARP table and let it recreate itself. It's something that I've done in the past on PLC systems, rarely required at higher levels. So that MAC address, you might see that when you're looking at some devices, and that MAC address can be used to uniquely identify the device. So sometimes it's like a serial number, but often many devices will have a separate serial number. But it is something that you will see on the network, particularly if you're doing these very low-level diagnostics using something like Wireshark. So what are you more likely to see? You're much more likely to see IP addressing. Again, IP addressing at a commercial level, you don't need IP because there are automatic addressing systems. But the IP addresses are defined on a per network basis, and they're expressed as 4 digits where each digit is a byte from 0 to 255. So what we do is we take the IP address and we split it into a network address, which could be something like 192.168.0, and then the remaining digits is the actual address of the device on the network. And then there's a related subnet mask, which defines which is the subnet and which is the network address. And if you're connecting to the internet, there will also be a gateway IP address. This is the address of the device on the network that connects to the internet or the wide area network. Now, if you're using a PLC system for performance, you probably will need to define IP addresses because PLCs don't normally have automatic addressing. There are some mechanisms like BootP, but they're rarely used. So normally that means that someone has to define the network and configure those IP addresses. And there are local type networks. What you'll very often see on a local network, you will see a subnet of 192.168, and then maybe a subnet mask, which is 255.255, and then that leaves you two more digits, which is the actual address. And you can define how that subnet mask works to define what the other addresses will be. And then your gateway performs what's called network address translation, and it translates internet addresses into your local area network addresses. So you may have to define that yourself, but more commonly, the IT administrator will have a DHCP server, and DHCP is Dynamic Host Configuration Protocol, and the administrator defines the subnet and the IP address range. And what happens is when you connect your computer to the network, it will issue a DHCP request, and then it will receive an IP address allocated automatically by the DHCP server. As I say, most commercial networks and home networks, that's how it's done. You very rarely need to configure an IP address. The only issue is potentially you could run out of IP addresses, but even that's quite unlikely. As I said, with PLCs though, they normally don't use DHCP. So for those, you do have to use what's called a static address, and you have to configure it accordingly. So every device on the same network must have the same subnet and subnet mask, but they must have a unique IP address. And there are some special addresses. So addresses ending 0 and 255 are not allowed. 255 is used for broadcast and 0 is just not allowed. And there are some subnets that are restricted as well. So often you'll see something like 192.168.0. That's a common subnet allowing up to 254 devices using addresses from 1 to 254. So here's an example of IP addressing for a PROFINET network. I've addressed the controller as 192.168.0.100. I've addressed the first I/O device as 192.168.0.101. The next device is 102, and the next device is 103. So for my IP addressing to work, I need to define my subnet, which is 192.168.0, and my subnet mask. This is the set of bits which we configure to define what's part of the subnet and what's part of the address. So I've got 255.255.255.0 as my subnet mask. And if you were to draw that out in binary, you'd see how that corresponds to the subnet and the addressing on the network. So it's for a smaller network, it's very straightforward. In this case, we've got no gateway in use. We don't need to worry about gateway address. So the subnet switching is quite simple. I have used some systems which do need a gateway IP address, even if there isn't one. So you could then assign something like 192.168.0 to 254, even if that device doesn't exist. So here's a similar IP addressing scheme, but this time for HMI SCADA, and we have got a connection to the WAN or to the internet using a router. So for this one, I've got my HMI SCADA server, for which I've chosen an address of 192.168.0.50. I might do this because I want this to coexist with my PROFINET network, or it might be a completely different network. But doing this just means that the devices don't overlap, just in case they were accidentally connected to each other. I've got a switch. No IP addresses on the switch, by the way, because this is an unmanaged switch. If it was a managed switch, it would have IP addresses, or at least one IP address. And then we have two clients, and I've addressed those at addresses 61 and 62. They don't have to be at these addresses. These are entirely arbitrary within my addressing scheme. But I've just given space in case maybe we want to add an extra SCADA server, or maybe I want to add a database server, or maybe some other devices. That gives me a gap from 51 to 60 before I get to my clients. And then I've got my router. In this case, my router is addressed at 192.168.0.1. So that has to be included in the IP addressing in case the SCADA server or the clients want to access the internet. So I've got an extra configuration item here. My subnet same as before, 192.168.0. My subnet mask the same as before, because that's identifying the subnet being the first 4 bytes. Or if you were to draw it out in binary again, it would actually be the first, what would we have? It would be the first 24 bits would be on there, the most significant 24 bits. And now I have to add the gateway, which is 192.168.0.1. You could, if you wanted to, configure a device on the network as a DHCP server and have all of this set up automatically. Usually the router is always a static IP address, but you could define the HMI SCADA server and clients using DHCP. But again, it would depend on your SCADA software as to whether that would be allowed. And there's also a potential performance issue. If you're converting MAC addresses to IP addresses and vice versa, that does mean that you need this ARP resolution. That does take a bit more time for processing. It's not a huge amount. In fact, it's probably negligible, but it needs to be considered in high performance networks. It also means you need more powerful devices, and that's typically why PLCs and I/O don't support DHCP. It's because they don't have the power to do that. Having said that, I've used quite a few modern I/O devices, and you can configure them for DHCP. They're powerful enough now that it could be done. But in the past, we just didn't have the computer power at that level to be able to do that. So this is what it looks like if you were using a DHCP server. In this case, my router is also my DHCP server. So that's got a static IP address of 192.168.0.1. So I define my subnet as 192.168.0. My subnet mask, same as before. My gateway address, same as before. But now what I also need to do inside my DHCP server, I need to define an IP address range. But I don't define any IP addresses at the HMI SCADA server or at any of the clients. They pick up an IP address that's automatically assigned when they turn on. And then typically they keep that address for a fixed amount of time. It's called a lease. So they would lease an address from the DHCP server, and they would keep that address for, depending on how the DHCP server is configured, it could be for hours, it could be days, or it might even be permanent if no other device is never added. But that's completely transparent to you as a user, that the DHCP clients, they issue the DHCP request on the network, the DHCP server responds with the details, and then they automatically update their ARP tables, and everything is transparent. So the good news for you as a user is, with this arrangement, you'd only need to configure one device. However, depending on what the other devices are, they may need that static IP addressing. But this is becoming increasingly common, just to have one device as a DHCP server, and then every other device on that network is a DHCP client. Now, DHCP is used to configure IP addresses. We also have devices these days with a name, and there's an additional protocol and process called DNS, or domain name server, which assigns names to each device to make it easier to track. In the previous slide, you would be able to see the IP addresses on the network, but you wouldn't know which was the server and which was the client device, and you may need to know that. Or some HMI SCADAs, they need to use that name so that they can access the services from the relevant device. So what you do is you assign a name to each device. So for example, if you're installing Windows, it automatically configures a name, or you can assign a name manually that might be more meaningful for you. And then what happens is inside the system, the DNS server keeps track of the names and the IP addresses. And then that can mean that when you look at messages on the network, you can see the name of the computer as well as the IP address. So it just makes it easier to work out what's going on your network. And also it can help for security reasons, because in your firewall, you can assign IP address tracking, but you can also restrict by the computer names as well. And the DNS, it can be configured as part of DHCP, or it may be hard-coded, or often it is a separate server. And typically, if you're installing a Microsoft system, part of your Active Directory or your domain server, one of those would be a domain name server as well, to keep track of all the names. So DNS, used because humans don't like numbers, we prefer names, but it also relates into that cybersecurity aspect as well. So here's what a system with DNS might look like. Same as before, but now we've also configured DNS. One of the reasons for using DNS for those names, particularly if you're going out onto the internet and you're trying to access devices on the internet, you may know the IP address of the name, but you may not. So for example, if you're using a search engine like Google, you normally type in google.com. But that google.com name does translate into a server IP address at some point. If you don't know what the IP address is, then you can't connect to it, and that's where DNS comes in. So with this system here, we don't have a local DNS server. We're actually using Google's DNS servers. So everything's the same as before. Yeah, we've got our SCADA server clients, which are DHCP clients and configured automatically. We've got our router out onto the internet. And now what we do is we configure the DNS server, and these are the numbers for Google's DNS server. So they've actually got two servers. They've got a primary DNS server, and they've got a secondary or backup DNS server, just in case the first one went down for any reason. So the primary server would be configured within your computer's 8888, and the backup server is 8844. And to be precise, I should use the dots between them, which is part of the IP addressing range. So it should be 8.8.8.8 or 8.8.4.4. So those are actually configured in the DHCP server, so they're automatically populated inside the HMI SCADA server and the client. And then that allows this HMI SCADA server and client to be able to access internet resources using your standard HTTP type name in your web browser. Again, DNS can also be used locally as well, because you might want to use local computer names, and that's where you'd have your local Active Directory server, which could have the local computer name as well as being able to access those internet names. So we mentioned cybersecurity. A bit more about cybersecurity. It's the practice of protecting a network against hacking attacks, also known as bad actors. And there are lots of things that hackers can do. They can interfere with network operation, which makes devices unavailable. This is often known as a denial of service attack. Or if the attack is launched from multiple computers, you might hear about DDoS, which is distributed denial of service. So DOS or DDoS. That's one thing that can do. So that's a simple lowest level of hacking, is just make it so you can't access your computers. This is normally pretty easily picked up on, and by blocking where the denial of service is coming from, that stops that denial of service from working. And it's pretty easy normally for the IT team to understand that and block the devices. This is where DDoS is harder, because you might be talking about hundreds or thousands or even tens of thousands of devices that all sending messages, which can make life a lot harder. But even that can normally be pretty easily blocked these days on a wider network. But that's like the base level of what a hacker can do. Interfere with network operation and ultimately plant operations, stop your manufacturing or stop you being able to do what you do by making those devices unavailable by disabling the network. Another thing they could do is modify packets on the network and cause unintended operation. I've done this experiment with Modbus TCP. Normally with Modbus TCP, you expect there to be a master device that sends requests and slave or server devices that respond to those requests. It's very easy for someone to put an external packet on the network that duplicates what the master device does, and you could write to those slave devices. Now Modbus TCP doesn't have any security on it, so you could potentially turn a PLC off, or put it from automatic into manual mode, or write directly to I/O if you had access to that level of the network. So modifying packets on the network and causing unintended operation, that's pretty serious. But having said that, most of the time you would be blocking those ports. To stop Modbus traffic on your network, you just block port 502, and that's it. You fix that problem. So the firewall resolves that issue very quickly. If someone was on your local network, of course, that's a different story. So you also need to think about how are you going to protect your network from internal bad actors as well as external ones. Now, people might want to steal data. Again, maybe they're not trying to write to your devices, but they may be able to pick up that data. Understanding what's going on inside those Modbus packets, that might be enough to understand what the throughput of that machine is. So you might understand, is that company producing today? Based on what they're producing, how many orders have they got? Is the machine running flat out or is it idle? Yeah. So that sort of data could be useful to a hacker or particularly a competitor who's trying to understand what you're doing. And then the other thing that hackers try and do is they actually try and access the devices themselves. They might want to stop them from operating by overwriting system files. They might want to install their own software, which is where these distributed denial of service attacks come from. They might want to steal data from the device rather than off the network. Or again, they might want to be inside the device and cause unintended operation. We see a lot of hacks these days where people are trying to access financial data, and also ransomware, where people lock the computer and then it's only unlocked when you pay a ransom. So there's a lot of serious threats which are the result of cybersecurity and we need to protect against. So with cybersecurity, there's a lot of things we need to do. There's a combination of passwords. We might want to sign the data. We might want to encrypt the data. And all of that helps us by stopping some of those above functions and preventing those hackers from being able to access our data and from being able to access our devices. Now, cybersecurity is a continually evolving subject, but one thing that really helps is a firewall. A firewall can block communications to restrict devices from accessing the network and devices on that network. Like I said, if you want to block Modbus TCP data, then a simple way to do that is a firewall at the higher network level that blocks any messages coming in on port 502. But it's not normally enough to have a single firewall. We're seeing evolution of how attacks work. It could be that the attacker gets into your network and does something on the computer that's inside the firewall, and then controls that computer inside the firewall to send your message using port 502. So it's not enough to block firewall port 502. You also need to block the other attempt and potentially block internal communications. So what we typically see today is networks have multiple firewall levels. There'll be a firewall which is connecting to the outside world at the router level. There might be firewalls between buildings and between departments. And then we may have firewalls which are part of the device and the operating system as well. So for example, if you've got a Windows computer, it's normally running a built-in firewall, either the Windows security system or maybe a third-party firewall. Typically what firewalls do is blacklist any address except specified addresses. So again, for example, to block Modbus data, you just block port 502. But a more common approach these days is becoming more and more to whitelist and only allow specified addresses. So port 502 might be open on your network, but what the firewall might do is say, I'm only going to accept messages from a device whose IP address is 192.168.0.101. So that gives you protection against another device on the network that's been compromised from being able to affect that device, because only messages from the registered address will be able to get through. Of course, if that registered address has been compromised, then you've still got a problem. But it's about defense in depth and having multiple options besides just the single firewall at the outside wall, which is what we used to have. Now, firewalls can also prevent against some hacking attacks like denial of service. If they see multiple requests from a single IP address, they can then block the IP address. And you can also get advanced devices. I mentioned deep packet inspection. Deep packet inspection is a way of looking at the packet on the network to see if it's legitimate. So again, when we talk about Modbus TCP, we've got the port, we've got the IP addresses, but we've also got the MAC addresses. So what deep packet inspection could do is look down at the MAC address level and see, is the device been on the network before? Is this a device I want to allow? And it could actually block that device, block that message based on something that's quite low level in that protocol. So deep packet inspection devices tend to be quite expensive, and you have to train them. Or maybe you could start by whitelisting a specific addresses. But if you want very advanced protection, then you get this combination of techniques, a combination of firewalls. You might also be using virtual private networks inside your network and virtual LANs, deep packet inspection. So there's a lot of devices there which can help protect your network from unauthorized access. So something that used to be more relevant, but less so these days because networks are getting so fast, is network transmission time. Data over the network is sent as bits, and typically we have that running over an underlying media. So if you're using copper, we're sending electrons, and with electrons, the speed of the electrons is approximately 2/3 of the speed of light. So if you look at the speed of light being 300,000 kilometers a second, the speed of the electrons is about 200,000 kilometers a second. And if you're switching the bits fast enough, the potential speed of light is not really a determining factor. The only time it becomes an issue perhaps is if you've got a very, very long network. But more likely over copper, it's not really going to be a problem. It's possible you would see problems where you have maybe slower radio waves, or maybe if you're using something like satellite communications. But generally the speed of the media is not normally an issue, except in very, very long applications, or in some legacy applications where you've got very slow media. For example, I used to work with some radio modems, and they had a speed of 128 kilobits a second. That 128 kilobits is not very fast by modern standards. So some older networks, that would be an issue. But with modern networks, you would maybe replace that today with a satellite network, which can run up to maybe a gigabit. So again, very fast. But there is an issue with delay or latency, but I'll come on to that in a minute. Now, assuming you've got a 100 megabit network, if you're sending 100 megabits per second, that means each bit on the network takes about 10 nanoseconds. If you add up the number of bits per byte, that gets you to 80 nanoseconds per byte. If you look at the minimum and maximum frames on the network, then you can see that we can send, the minimum time would be 7 microseconds, the maximum size would be 123 microseconds. If we take the average frame size, that would be about 65 microseconds, and that allows us to send over 15,000 frames per second, which is a lot. And that's between any two devices. Using a modern switched network, any two devices would be able to send that 15,000 frames per second. If you were using gigabit Ethernet, that multiplies by 10, and now you can send 150,000 frames per second. So what we're actually reaching here is we're reaching a period or a situation with 10 gigabit Ethernet, and particularly with 10 gigabit Ethernet, where the actual device itself can't cope. And this is what I mean about latency. Each device that switches the message takes a certain amount of time to send that message. You've either got to handle the message within your Ethernet device, or you've got to switch the signals in the switch. But now that's beginning to add up, and that latency can cause a problem in some very high speed networks. Not normally a problem for PLC networks, we're running in the milliseconds. Definitely not a problem when we're running at the order of maybe a few seconds when we're doing some internet request. It might be a problem if we're streaming video, particularly if we're streaming very high quality video, like high definition or 4K or even 8K video. But even then, generally the systems can cope quite well. But then, of course, we have to think about the actual device response time itself, and these are normally the slowest systems in there. If you've got a Windows-based system, it has to handle the message. If you've got an I/O device, then it's probably using an embedded CPU, and it's got even more processing work to do with a slower handling device, a slower Ethernet chip. So normally the speed of the network transmission, the actual speed, the time on the network is irrelevant compared to the actual device response times. So how do we construct a network? Often this is done for us. We would have an IT team or some sort of system development team. But if you're doing this yourself, what you need to do is you need to itemize all the components you're going to have. So that would consist of servers, clients, PLCs, I/O devices, and also any other sort of ancillary device that's on there. May include routers and gateways, may include security technology. But often, when we're constructing a network, we would normally subcontract this to a network expert. But if you're doing it yourself and it's a relatively simple network, you can do that. You itemize the components, you choose your topology, and then you can map out each device on a diagram. That could be hand-drawn. Maybe you're going to use PowerPoint or Visio, possibly a whiteboard with post-it notes. And then what you need to do is you need to check for limitations. So if you're creating a home network, unless you're living in a very large house, distance isn't normally going to be a problem because you've got a 100-meter limit on cables, assuming you can even buy a cable that long. I think the longest cable I bought for Ethernet was I think 30 meters. Or maybe 50 meters, but certainly well within the limitations of Ethernet. For wireless, of course, yeah, there may be additional limitations there, and particularly if you've got very thick walls, you might need to think about where you put your device. You might need to think about device limits or protocol restrictions. Yeah, again, if you're designing an industrial network, remember that PROFINET can't be routed, so every PROFINET device that wants to talk to each other has to be on the same physical network. And then what you do is you think about the network path from one to another. And a good way of doing this is trace the message through a network. First of all, you need to make sure it can reach its destination, but what you also need to do is make sure it can't reach its destination via multiple paths. And if there are multiple paths, then you may be looking at using media redundancy protocol or rapid spanning tree protocol. Those allow loops, but most networks don't. So this allows you to construct the network. Yeah, you break it down into all the devices you have, and then you build it up by adding the devices and working out how they're going to communicate. Of course, there will be physical constraints. Like I mentioned, if you've got Wi-Fi, you know, where are the brick walls which will absorb the signal? Where's the router going to go? Higher up is best, but you might not want it in a location where it's on the wall looking ugly. Cables, how are you going to route your cables? You know, so there are physical constraints as well, and they all need to be managed as part of the network. But for small networks, you know, it's pretty straightforward to design your own network and even to perform the IP addressing as well based on standard layouts. So I'm going to leave you with this network terminology slide. Networks can be quite complicated, and there's a lot of underlying theory as well as practice. But today, with modern technology, with modern protocols, creating these networks is generally quite straightforward.